Welcome to Gradient Daily, your daily deep dive into the most fascinating research papers in AI. Today we're diving into something really special. It's a paper that's fundamentally changing how we generate entire 360-degree immersive worlds from just a little bit of text. This is a huge challenge right at the intersection of computer vision and generative AI. And the paper we're exploring, DiT360, offers a solution that is just so clever and elegant. All right, let's get into it.
Okay, just take a look at these images for a second. This is the dream, right? The holy grail for so many fields. VR, gaming, architecture, you name it. The ability to just type a few words and create a completely photorealistic, geometrically perfect, panoramic world. But here's the thing. Making an image like this is a whole different ballgame than making a normal square photo. We're dealing with something called an equirectangular projection. The easiest way to think about it is like a world map. You know how you take a spherical globe and unroll it onto a flat rectangle? That's exactly what's happening here. And just like on a world map, this process creates some wild distortions. Greenland looks massive, Antarctica gets stretched across the entire bottom. The same thing happens here, especially at the very top and bottom, the poles. An AI model has to learn this incredibly weird, nonlinear geometry from scratch. And on top of that, it has to be absolutely perfect where the left and right edges meet. If there's even a single pixel out of place, the whole illusion of being in a seamless world is just gone. It's a massive, massive technical hurdle.
So the paper that steps up to this challenge is called DiT360, high-fidelity panoramic image generation via hybrid training. And check out the team behind it. It's a collaboration between Insta360 Research, a company that literally lives and breathes 360-degree cameras, and some absolute top-tier universities like Tsinghua, Nanyang Technological, and Wuhan. This kind of industry meets academia partnership is often where the real magic happens. And as we're about to see, their big breakthrough wasn't necessarily building a bigger, crazier model. Instead, they took a step back and focused on the data itself. This is a huge trend in AI right now. This idea that the biggest wins often come not from changing the engine, but from fundamentally changing the fuel you put into it.
All right, here's our game plan for today. We're going to break this down into 6 parts to really understand it. First, we'll dig a little deeper into the Panorama Problem. Then, we'll unveil DiT360's super clever hybrid solution. After that, we're doing a 2-part deep dive into their secret sauce, image-level regularization and token-level supervision. Then we'll put it to the test and see the results. And finally, we'll wrap up with a fair critique and a look at what the future holds.
Okay, so let's start at the beginning. Why is this so hard? Why is it so incredibly difficult for a computer to just dream up a convincing 360-degree world?
It really boils down to 4 huge headaches. First, as we mentioned, the geometry is a total nightmare for most AI models. Your standard models, like convolutional neural networks or CNNs, are built on this idea that a cat looks like a cat no matter where it is in the picture. But in a panorama, a straight line at the horizon looks completely different from a straight line near the ceiling. The model has to learn these bizarre context-dependent rules. Second, you have that problem of seamless continuity. The pixel on the far right has to be a perfect neighbor to the pixel on the far left. Any mismatch creates this jarring vertical line that just screams fake. Third, the goal isn't just a plausible world, it's a photorealistic one. A lot of older models made images that looked like, a skybox from a 10-year-old video game. It's technically a 360 view, but it feels flat and lifeless. And finally, we get to the absolute heart of the problem, the one DiT360 really attacks. There's just not enough good data. Think about it. There are billions, maybe trillions, of regular photos on the internet. But high-quality, well-labeled, 360-degree panoramic images? The number is tiny in comparison. This data scarcity has been the single biggest roadblock holding the whole field back.
And this isn't just theory. You can see it with your own eyes right here. On the left, this is a result from a previous leading model. Look inside that red box. See how the structures on the ceiling are all warped and blurry? It's like the AI just gave up trying to figure out the geometry out there. The whole thing feels kind of flat, kind of CG. Now look at the right. This is DiT360, given the same prompt. The difference is just staggering. The lines are clean, the geometry is solid, the details are tack sharp, and the whole scene just feels real and coherent. This single comparison shows the massive leap forward they've made. So the big question is, how on earth did they do it?
So how did they pull it off? This brings us to the core idea of their paper, this new data-centric way of thinking. Instead of just trying to build a bigger, stronger model to brute force the problem, they decided to get smart and fix the data problem itself.
And I love this because they say it loud and clear in the paper. This quote is everything. We attribute the main reason to the lack of large-scale, high-quality, real-world panoramic data, where such a data-centric view differs from prior methods that focus on model design.
This is a huge statement. They're telling the whole research community, hey, maybe the bottleneck isn't the engine, maybe it's the fuel. It's a powerful reminder that sometimes the cleverest solution isn't a more complex algorithm, but a more intelligent approach to the data you're using. And their solution is this beautiful strategy called hybrid training. The logic is so simple, but it's totally brilliant. They said, okay, we have a scarcity of panoramic data, but we have a massive abundance of regular, high-quality photos. Can we use the abundant data to help with the scarce data? The answer is yes. They use the billions of normal photos to teach the model the fundamentals of photorealism. What does real lighting look like? What are the textures of wood or metal or concrete? Then they use the smaller, specialized panoramic dataset to teach the model the unique geometry of a 360-degree world. It's this incredible way of transferring knowledge from a data-rich world into a data-poor one. Okay, this diagram right here is our technical roadmap for the next few minutes. It looks a bit intimidating, but let's walk through it. See the two paths at the top? That's their hybrid philosophy in action. You've got a perspective branch for the normal photos and a panoramic branch for the 360 images. Both types of images get fed into what's called the VAE encoder. You can think of this as a compressor. It takes the image and turns it into a compact, latent representation, the model's internal idea of the image. The heart of the system is a diffusion transformer, or DIT. This is the creative engine. It learns to create images by starting with pure random noise, and then carefully removing that noise step by step until a clean image emerges. But the real magic, the genius of this paper, is in the two boxes at the bottom: image-level modules and token-level modules. This is their two-pronged attack. They make clever interventions at the image level, cleaning up the data before it even enters the model, and at the token level, which is inside the model's brain, to enforce the strict rules of panoramic geometry. We're going to unpack both of these right now.
All right, let's start with that first level, image-level regularization. This is all about data prep. You know the old saying, garbage in, garbage out? Well, it's 1,000 times more true for these huge AI models. The researchers here are basically acting as master chefs, making sure only the absolute best ingredients go into their recipe. First up, they tackle their own panoramic data. They're using a dataset called Matterport 3D, which is pretty good, but it has one big flaw. The tops and bottoms, the poles, are often a blurry, distorted mess from the way the cameras capture them. So they invented this awesome pre-processing pipeline to fix it. First, they take the weird panoramic image and project it onto the 6 faces of a cube. This is called a cube map. Now, why a cube? Because a cube is made of 6 perfectly flat, normal-looking squares. And we have amazing AI models that are great at fixing regular square images. It's a way of turning one really hard problem into 6 much easier ones. They then mask out the blurry parts of the top and bottom faces and use a powerful in-painting model to intelligently fill in the blanks with sharp, realistic details. Finally, they wrap that fixed-up cube map back into the panoramic format. The result? A much cleaner, higher-quality dataset that won't teach the model any bad habits. Now for the other half of the image-level strategy, using all those normal photos. This part is so clever. They take a high-quality photo from a huge dataset called Lion, and they digitally project it into the panoramic space. It's almost like they're cutting a window into their 360-degree world and pasting this perfectly photorealistic view inside it. The rest of the panorama is blank, but for that one section, the model gets this incredibly strong lesson. It's like giving it a perfect reference swatch and saying, hey, see this? This is what a real brick wall is supposed to look like. Learn from this. It's a powerful dose of realism that the model would just never get from the limited panoramic dataset alone. Okay, so they've meticulously cleaned up all their input data. That's a huge step, but that's only half the battle. Now we have to go inside the model's brain, to the token level, and teach it the fundamental laws of 360-degree physics and geometry. And this is where their custom loss functions come into play. So they introduced 3 brilliant mechanisms to enforce this geometric understanding. The first is super simple, circular padding. It basically tells the model that the left edge and the right edge of the image are connected. Think of it like a perfectly looping GIF or a seamless wallpaper pattern. It explicitly forces the model to pay attention across that boundary, which guarantees you'll never get that ugly seam. The second is called yaw loss, and this is wild. A yaw is just a horizontal rotation. They take a scene, digitally rotate it, and then check if the model's understanding of the rotated scene is consistent. It's like sitting the model in a spinning chair and asking it to describe the room. Its description has to stay consistent as it turns. This forces the model to build a true 3D mental map of the scene, not just a flat 2D picture. And finally, the big one, cube loss. This is their ultimate weapon against the distortion at the poles.
Instead of just grading the model on the weird, stretched-out panoramic image, they also project its output onto a clean cube map and grade it there too. It's like telling a student who has only ever seen flat world maps, okay, your map looks good, but now let's wrap it around a real 3D globe and see if it still makes sense. This forces the model to learn the rules of the projection so it can generate geometrically correct poles instead of just copying the blurry mess it saw on the training data.
And here is the proof, right here. On the left, you see a bathroom generated without cube loss. Just look at the ceiling. See that vent? It's all swirly and distorted, like something out of a funhouse. The model is just guessing. Now look at the image on the right. This was generated with cube loss. Bam! The geometry just snaps into place. The lines are straight, the perspective feels right. It's a night and day difference. And it's all because of that one clever trick of grading the model's work in the clean, geometrically correct cube map space.
So the theory is beautiful. The components all seem to make sense. But does it all actually work when you put it to the test? Let's check out the results and see how DiT360 stacks up against the other big names in this space.
And here we have the visual showdown. Let's just go down the list here. Look at the results from the other models. You see all kinds of issues. Warped buildings, repetitive textures that look copy-pasted, blurry details. Hunyan World does a decent job with geometry, but it still has that slightly synthetic CG look. It just doesn't quite feel real. Now drop your eyes to that bottom row. DiT360. The images are consistently sharp, the architectural details are crisp, and most importantly, they just feel photorealistic. The lighting, the textures, it feels like a real place. Visually, it's just playing in a completely different league. And the numbers absolutely back up what our eyes are telling us. Now, don't get scared by the table. The only thing you need to know is that for all these scores, lower is better. Let's look at FID. That's the standard score for realism. DiT360 gets the lowest score, so it's the most realistic. Simple. Now look at FID poll. This is a special metric they invented to only score the quality of the top and bottom of the image. And look at that. DiT360 wins by a mile. This is the hard data that proves their cube loss idea is a massive success. Then you have things like Brisk and Nike. You can think of these as automated art critics that look for any technical flaws in an image, like blurriness or weird artifacts. And again, DiT360 scores are just dramatically better than everyone else's. The numbers don't lie.
Now, this is one of my favorite parts of any really solid research paper, the ablation study. This is where the scientists take their beautiful new model and they start systematically pulling out pieces to see what breaks. It's how you prove that every single component you added is actually doing important work. So top left is the baseline model with none of their tricks. It's a mess. You've got discontinuities, weird distortions, all sorts of problems. Then they add their ideas one by one. Add circular padding, boom, the seam at the edge disappears. Add cube loss, boom, the weird distortions at the pole get fixed. Add yaw loss, boom, the overall scene becomes more coherent. It proves that there's no single magic bullet here. It's the careful combination of all these clever ideas working in harmony that creates that stunning final result.
Okay, so we've established that DiT360 is a huge step forward, a new state-of-the-art. But of course, no research is ever perfect or finished. So let's take a step back and give this a fair, balanced critique and talk about where this is all going.
So the strengths are pretty obvious. This model is the new king of the hill for making realistic panoramas. And the core idea, hybrid training, is a fantastic gift to the entire AI community. It's a strategy that could be used to solve all sorts of data scarcity problems. But the authors are also really honest about the limitations. The model is still at the mercy of its training data. For example, it really struggles to generate realistic human faces. And why is that? Well, because the Matterport 3D dataset is mostly empty rooms and landscapes. There just aren't many high-res faces for it to learn from. And that points us directly to the future. Step 1 is obvious. We need to collect more and better panoramic data, covering a wider range of subjects. And then, the long-term dream, the holy grail, is to extend this from generating a 2D spherical image to generating a full, walkable 3D scene. This paper is a critical, foundational step towards that incredible future.
And that leaves us with a really big question to think about. This paper did a brilliant job of bridging the gap between normal 2D photos and panoramic images. So what's the next big gap AI needs to cross? Is it from static images to dynamic video? From 2D and 3D representations to a true understanding of physics and causality? It's a huge and exciting question, and it's what researchers around the world are working on right now.
All right, so if you only remember 3 things from today's deep dive, let it be these. Number 1, data over design. Sometimes a smarter way of using your data is way more powerful than just building a bigger model. Number 2, supervision at all levels. The best results came from a full stack approach.
fixing the data on the way in, and teaching the model the rules on the inside. And number 3, learning from abundance. This is a big one. You can often solve a data shortage in one area by finding a clever way to borrow knowledge from a related area where data is plentiful.
And that is our deep dive on DiT360. What an absolutely fantastic paper. If you enjoyed this breakdown and learned something new, it would be amazing if you could hit that like button and subscribe to Gradient Daily. Oh, and make sure you ring that notification bell so you don't miss what we're covering tomorrow. We are back every single day with a brand new paper. Thank you so much for your time, and I'll see you tomorrow.